For this lab, we had to observe an object free-falling from rest.
Physics involved would be that delta V equals force over mass times delta T. And the force that we're talking about here, since the object is free-falling, the only two forces acting on the object would be the force of gravity and the force from drag. F drag equals negative b times the vector v squared times the unit vector for v, where v is the velocity and b is a defined constant. I entered in my data into Tracker after dropping a container of bay leaves. I used a notebook as a calibration because I know that notebook is exactly 0.2794 meters. I set the x-axis to be positive in the down direction, so I rotated the axes by 90 degrees to the right. And after I did this, I had all my data, so I entered the necessary stats into VPython to get the model so I can compare that to the positional data that I extracted from Tracker. The mass of the object that I used was 8 grams, and the acceleration due to gravity is negative 9.8 in the y direction. As you can see here, the force that I used was the sum of the acceleration force and the drag force. The acceleration force is negative 9.8 times the mass of the ball, and that would be in the y direction. Also, to go with that, the drag force is the same as the equation that I just mentioned earlier, and you can see that how I implemented that here. The resulting model with drag force added in is as shown. Before this, I did a model without drag, and all of that data shall be shown soon, but the final position was negative 0.957359 meters in the y direction. The x direction doesn't matter because the object didn't move in the x direction. And here we can see all three of the different versions of this experiment, where we have the Tracker data, the model without drag, and the model with drag. As you can see, the model without and the model with drag are both very close together, and both of them are very close to the Tracker data. There is seemingly one spot where the data does not match up quite as perfectly. However, that is most likely due to human error when placing the points in Tracker. However, the whole thing is very close.
Next, I graphed the velocity with respect to time, and as you can see, this graph is a curve which suggests that there will be a terminal velocity, which makes sense because you have the drag force, and you also have the force of gravity, and the drag force is going to make it so that there is a maximum velocity that can be reached. The only plots that seem to suggest that there will be a terminal velocity are the real-world plot and the model that includes drag force, which makes sense because you need a force in the opposite direction for there to be a terminal velocity. Also, if the object were to be thrown downwards, all you would be doing is changing the initial velocity, and as the graph above shows, if you change the initial velocity, you do not change the fact that there's going to be a terminal velocity. In fact, all that you're doing is changing where in the graph you're starting at. The terminal velocity will still be the exact same. And that's my lab.